This question is asked in gate 22 of ECE. This is from control system subjects and from the Nyquist plot topic. The question is, consider a closed loop control system with unity negative feedback and KGS in the forward path where gain K equals to 2. The complete Nyquist plot of the transfer function GS is shown in the figure. Note that the Nyquist contour has been chosen to have clockwise sense. Assume GS has no poles on the closed right half of the complex plane. The number of poles of the closed loop transfer function in the closed right half of the complex plane is dash. Okay, so let us first see what data is given. Okay, so basically it's a unity negative feedback structures is what is being said in the questions. So this side is plus, this side is minus, this is your unity negative feedback, and the transfer function is K into G of S. Okay, this is what is the data given in the question. Okay, but so it is KGS in general, but here it is said the gain is K equals to 2. That means this particular transfer function should be 2GS if I substitute K equals to 2. One more data is given. The complete Nyquist plot for the transfer function G of S is shown here. Okay, so this is the plot for G of S, or you can say this is the plot of KGS with value K equals to 1. So the original plot which is given in the question, that is with respect to K equals to 1. Okay, but the question is framed with respect to K equals to 2. This is a small trick here. You should be careful because they have said it is K equals to 2, but the data is given with respect to K equals to 1. I mean the plot. Okay, so first thing is we have to modify the plot. So what is the changes that we'll be getting in this plot if I take K equals to 2 instead of 1? Okay, we'll see that. Note that the Nyquist contour has been chosen in clockwise sense. So this is the as usual assumption what we make, nothing much to say about it. So again one data is given. Assume GS has no poles on the closed right half of the complex plane. That means, like the standard Nyquist stability equation N is equals to P minus Z, where P indicates the number of open loop poles in the right half of S plane. That is what is 0 here. So your P equals to 0, right? No poles on the closed right half of the complex plane for GS. So GS is what? GS is the open loop transfer function. So G of S having no, poles lying on the right half of S plane. That means P equal to 0. So if P equal to 0, if I substitute in these equations, then I get N is equals to minus of Z, or Z is equals to minus of N. But what is this? What we need? We need to find the number of poles of the closed loop transfer function in the right half of the complex plane. So that is nothing but the value of Z. So in this equation N equal to P minus Z, P indicates the number of poles of the open loop transfer function in the right half of S plane. Z indicates the number of closed loop pole in the right half of S plane. So here it is given that P is 0 and we need to find Z. Z means the number of closed loop poles on the right half of S plane. So basically we have to get the value of N. So negative of that will be my answer. But what is N? N is the number of encirclement about the point minus 1 plus J0. So we'll be finding, the encirclement about N equals to, we'll be finding the encirclement about the critical point minus 1 plus J0. That's value is N. So negative of N is the answer. Okay. So first the point is, so this plot is given with respect to K equals to 1. But if I say, okay, forget about K equals to 1. If I tell you to show me the plot with respect to K in general. So what is the change? The change is, so which is minus 1. So this is minus 1 into K. And this is, which is 0.4. This is 0.4 into K. And this is 0.8 into K. Okay. I mean the length which are specified. Or to be very specific, this location is nothing but equals to your minus K. This location, okay, which is 0.8K, that will be the left side. So this will be minus 0.8K. And this location, which is, minus 0.4. So this is your minus 0.4K. So this is what is in general with respect to K, any value of K. But we need K equals to 2. So if I take K equals to 2, that means this value which is minus 0.4K. So this is your minus of 0.8. So this value which is minus 0.8K, this is your minus of 1.6. And this value which is minus K, so this becomes minus of 2. Okay, so to write in a more cleaned way, so let me show these points what I said. I am saying this point is no more minus 1. So this point is your minus of 2. This point which is minus of 0.8, okay, minus of 0.82 is minus of 1.6. So this location coordinate is minus of 1.6. This location coordinate which is minus 0.4k. So this is your minus of 0.8 if I take k value equals to 2. But what is our requirement? We want to find the value of n, that is the number of encirclement about the point minus 1 plus j0. But where is this minus 1? So if you concentrate, so this is your 0, this is your minus 0.8, this is your minus 1.6. So where this minus 1 will come? This minus 1 will come somewhere here, right? Because this is minus 0.8, this is minus 1.6. So minus 1 will be coming somewhere between this node and this node. So now I'll be finding the number of encirclement about this critical point minus 1, right? So if I observe, if I put a line like this, so this line is intersecting the plot 2 times. One is at this point, one is at this point. And both are in the clockwise directions. So if it is in clockwise directions, we count it is minus 1. Anti-clockwise means we count it is plus 1. So the value of n is nothing but equals to minus 2 in this case. Why? Because this line is intersecting the plot twice and both are in the clockwise directions. If the direction would have been anti-clockwise, I would have taken n equals to plus 2, but because of clockwise, I am taking n equals to minus 2. And that's what we need. Z is equals to minus of n. So minus of 2. So Z equals to 2. Okay. So the number of closed loop poles on the right half of S plane is nothing but equals to 2. So 2 is the right answer for this question, which is given in option C. So this is also, not a tough questions, but yes, there is a chance of mistake if you are not identifying that the plot is with respect to GS and the question is with respect to 2GS. This is a small catch, otherwise there is nothing much concept involved in these questions. Answer is option C for this. This question is asked in gate 22 of ECE. This is from control system subject and from root locus. The question is the root locus plot of a closed loop system with unity negative feedback and the transfer function kgs in forward path is shown in the figure. Note that k is varied from 0 to infinity. Select the transfer function g of s that results in the root locus plot of the closed loop system as shown in the figure. So basically the k is varying from 0 to infinite. That means it is not inverse root locus. This is direct root locus. That's what they want to tell, right? And nothing much given in the question. So based on this particular plot, we have to identify which transfer function of these 4 options will result this kind of root locus. So the key point to note in this particular root locus plot is, so from this particular point, there are 5 root locus branches are emerging. 1, 2, 3, 4 and 5. So when is it possible? So from a single point, 5 root locus branches are emerging out. So this is possible only when there are 5 poles located at the same point. Yes or no? Then only from that point itself, the root locus branch will emerge out and you will have this kind of plots. So the requirement is to satisfy this particular situations, there should be 5 poles should be lying at this particular point. So which of the options is showing that one, like 5 poles at a single locations? Definitely that is option A only. Right, because if you see this is a 5th order pole at minus 1, at s equals to minus 1, there are 5 poles located. So this is not the situation B, and this C is saying there are 6 poles. We don't need 6 poles, because if the branches would have been 6, then there could have been a possibility of C as well. But as far as this is concerned, we have 5 branches. This is also not possible. Similarly, this is also 6th order. It doesn't make any sense. So the answer is option A for this. We don't need, like, how is it s equals to minus 1? It can be minus 2, minus 4. So that is not the point in this case. Qualitatively, you have to give the answer. So the given situations, what is being given, that has to be satisfied only by option A. So this is also a common sense based questions. We need hardly, 30-40 seconds to tell the answer. Answer is option A for this. This question is asked in gate 22 of ECE. This is from control system subject and related to the RH criteria concept. The question is, consider an even polynomial P of S is given, where K is unknown real parameter. The complete range of K for which P of S has all roots on imaginary axis is dash. This questions you may solve using the concept of maths. You may let the S square value equals to X. So you will get the quadratic equations like X square plus 5X plus 4 plus K equal to 0. You can solve that one and you can exactly find what are the 4 roots of this. That is, what one approach. You can go by normal math. So let's go by the control system concept here, right? We are not interested to solve this using a math concept. So such kind of questions are generally solved by RH criteria, right? So let me make the RH table. So it's a fourth order equation. So in the table, my first row is S power 4, next row is S power 3. So what is your S power 4 coefficients? I mean the even order coefficients is 1. So next is 5, next is 5, and next is 4 plus k, right? So because this coefficient is 1, this coefficient is 5, and this is the constant, that is the coefficient of S power 0 is 4 plus k. So all the odd order power of S are missing. So that means those are 0, 0, and 0. So what you do when you get the row of 0, so the equation above the row of 0 is the auxiliary equation. So we used to differentiate the auxiliary equation and the corresponding coefficient we used to substitute in the row of 0. So that means what is the auxiliary equation here? This is what the auxiliary equation. So differentiate the auxiliary equations. Okay. So if you differentiate the auxiliary equation, so it is 4s cube. That means I am differentiating this equation. 4s cube plus 10s plus 0. So these are coefficient, that is 4, 10 and 0. I'll be replacing in the row of 0. So this 0 is replaced with 4. This 0 is replaced with 10, and this is anyway it is 0. Usually in most of the cases we get the row of 0 after completing 2-3 row we used to get, but here in the beginning itself the row of 0 we are getting, but no problem, we can again continue the same approach. Next is S power 2. So how do we get? So 4 into 5. So 4 into 5, 20, minus 10 into 1, 10. 20 minus 10 is 10. 10 divided by 4 is 2.5. Next, 4 into 4 plus k into 0 into 1 is 0 divided by 4. So this is basically your same 4 plus k only, right? This is 4 plus k and this is 0. Now what is S power 1? So S power 1 is 2.5 into 10 is 25 minus 4 into 4 plus k. So let me do here 25 minus 4 into, so this is 16 minus 4k divided by 2.5. So 25 minus 16 is 9. So here you get it is 9 minus 4k divided by 2.5. Next, what do you get? 2.5 into 0 is 0. Okay, this is 0. And then I have S power 0. So if S power 0, if you see this into this minus this is anyway 0 divided by this. So this is basically 4 plus k. So this is what is the RH table. And here, what is the condition? Okay, so P of S has all roots on the imaginary axis. So you need this condition. So you have to find the value of k in such a way that the roots of this polynomial will be in the imaginary axis. That means we expect row of 0. We expect row of 0, right? So row of 0 if you expect, and that to be in terms of k, what are the options you have? You have very, very clearly. So because this is anyway, we don't have the row of 0. We don't have row of 0. This is 2.5. We cannot make it row of 0. So the only option that is left is you can make this as 0 and this as 0 so that it becomes a row of 0. So for that, what I'll be doing is, so first is I will be equating this 9 minus 4k divided by 2.5 equal to 0. So 9 minus 4k equals to 0, or 4k equals to 9. Okay. Or your k is equals to 9 by 4. So one of the value of k, I mean, I'll be substituting here, that is 9 by 4, so that it will be row of 0. Another value is you have to equate this 4 plus k equals to 0. So 4 plus k equals to 0 means k equals to minus 4. So if I substitute k minus, this will be row of 0. So that means two specific value of k, which is making row of 0, is 9 by 4 and minus 4. So the range of k, okay, so this is limited in the range of minus 4 to 9 by 4. At these two boundary value, we are getting it is row of 0, so which imply that the roots will be on the imaginary axis. But whether the roots will be in the, whether the, poles will be, how they will be single or repeated, that again depends. but that much of specific details is not required in this question, so we don't want to go into that. So if I check, this is given option A, so A is the right answer. So this is again a very simple and straightforward questions. So you need hardly 2 minutes of time because of the calculation to get this. Otherwise, conceptually nothing new. Some of you might be getting surprised, like how do you proceed in the first step? Because usually most of the cases what we solve the question in the classes, we get the row of 0 after 2-3 rows. But here in the beginning itself it is there, but again the concept remains same. So the answer is that between -4 and 9, which is option A. This question is asked in gate 22 of electronics. This is from control system subjects and from time response analysis topic. The question is, two LTI system with transfer function G1s and G2s have unit step response y1t and y2t respectively. Which of the following statement is that true? Okay, so the options are y2, ytt have same percentage of peak overshoot. Second option is saying they have same steady state value. Third option is saying they have same damped frequency of oscillations. And the fourth one is saying they have same settling time for 2% tolerance. So basically, some data that you need in this case. So peak overshoot, as per as the option A is concerned, peak overshoot is function of zeta only. E raised to power minus pi zeta divided by square root of 1 minus zeta square into 100. So peak overshoot is what? Function of zeta. Second option B, they have same steady state values. So steady state value y of s by finite value theorems. Okay, steady state value means it is nothing but y of infinite. So this is given by limit s tends to 0, s into y of s. So s into y of, what is y of s? Step response they are asking, right? Step response. So it is 1 by s into g of s. So this is equivalent to limit s tends to 0, g of s. Limit s tends to 0, g of s. Third option is saying y1, y2 to have same damped frequency oscillations. Damped frequency omega d is equals to omega n into square root of 1 minus zeta square. Okay. So, and the fourth case, they have same settling time for 2%. For this is basically 4 by zeta omega n. So the Ts is functions of zeta omega n. Okay. So basically, if you see, we need the data of zeta and omega n. And by the way, there should not be any confusion. So these are the direct transfer function. That means you can think of this is what nothing but the closed loop transfer function given. This is g of s. Input is 1 by s, and this is what your output, because ut in the s domain is 1 by s. So if I compare the denominator with the standard characteristic equations of second order system, so what do you get? So in the first case, okay, in the first case you can see for system 1 you can see. So if you compare, your omega n is coming as 1, because this is omega n square. Omega n is basically 1. Then 2 zeta omega n is 1, right? Then 2 zeta is equals to 1. That means your zeta is equals to 1 by 2. So for the system 1, the data is, so for the system 1, omega n is 1 and zeta is basically half. This is for system 1. For system 2, what is your omega n and what is your zeta? So for system 2, what is your omega n and what is zeta? So for system 2, omega n square is 10. So omega n is square root of 10. Then if you compare, then 2 zeta omega n is equals to square root of 10. So omega n is square root of 10 into 2. So we need zeta, right? Sorry. Then zeta is equals to square root of 10 into 2 omega n. That is 2 square root by 10. So this is coming half. So zeta is coming half for system 2. So this is what is the data, right? So by comparing the characteristic equations, we came to the conclusion omega n are different for systems. This is one case, and one case it is square root of 10. But zeta is same for both of the cases. Now let us verify each options. Option is saying y1t and y2 have same percentage of peak overshoot. Option A is definitely correct, because if both system have same zeta, zeta is half, then naturally their corresponding peak overshoot will be same, because the formula is e raised to power minus pi zeta into square root of j square, this whole multiplied by 100. So this is only function of zeta. If you substitute zeta equals to half, which is true for both system, so definitely their corresponding answer will be same. So first answer is correct. Okay, now coming to the second one. What is second one saying? Y1 and Y2 have same steady state value. So the steady state value Y1 of infinite is limit s tends to 0. So it is G1 of s. So that is 10 divided by s square plus s plus 1. If I substitute s equal to 0, that is coming 10. Similarly, Y2 of infinity is limit s tends to 0. And this is 10 divided by s square plus s square root of 10 plus 10. So if you substitute s equal to 0 in this equations, so this is coming as 1. So y1 of infinite is basically 10. Okay. So the steady state value of y1t, so that is y1 of infinite we got it is 10, but y2 of infinite we are getting it is 1. Isn't it? So naturally the steady state value are not same. So option B is wrong. Option C, y1t and y2t have same damped frequency of oscillations. So this will be wrong also. Why? Because damped frequency of oscillation is omega n into 1 minus zeta square. So although this zeta is same for both of the cases, but omega n is different. So this 1 minus zeta square root of this will be same for both cases, because omega n is different. Then naturally it means omega d1 is not equals to omega d2. But what the option is saying, they have same damped frequency. No, they don't have same damped frequency. So option C is also wrong. Option D, y1t and y2t have same 2% settling time. This will also be wrong. Why? Because settling time is 4 by zeta omega n. Do you think the zeta omega n product for both of the cases will be same? It's not, because zeta omega n for first case it is half. For the second case it is square root of 10 by 2. Because zeta omega n product is not same for both cases. How they have the same settling time? This is also wrong. So in this case, only one option, option A is correct. So this is basically formula based questions. The question appears to be a MSQ, but it's in this case only one of the option is coming correct, which is option A. So basically, if you know the basic formula, omega n zeta and settling time, peak overshoot, damp oscillation frequency formula, then by computing zeta omega n for both cases, you can easily figure it out which options are correct or wrong. In this case, only option A is true, remaining are false. This question is asked in gate 22 of electronics. This is from control system subjects and related to the steady state error concept. The question is, the block diagram of a closed loop control system is shown in the figure. Rs, Ys and Ds are Laplace transform of time domain signal Rt, Yt and Dt respectively. Let the error signal is defined as Et equals to Rt minus Yt. Assuming the reference input Rt equal to 0 for all time, the steady state error E of infinite due to a unit step disturbance dt is dash, rounded up to 2 decimal places. So one thing is given in these questions. Okay. So as far as the notation is concerned, so this is your R of S, this is your Y of S, and Et is given as R of t minus Yt. That means E of S is R of S minus Y of S. So this is the outcome of this summation point is basically E of S. That's what they are saying. Okay. And assuming the reference input 0, so I'll be making this Rs equal to 0. We'll make this, that's what is given. Then what is this steady state error? E of infinite. So using the final value theorems, E of infinite is nothing but limit s tends to 0, s into E of s. So I have to get what is E of s first, then I'll be substituting here to get the corresponding answer. Well, but here the error you have to find the steady state error E of infinite due to unit step disturbance. That means you have to think this d of s is the inputs and you have to think this E of s is the outputs. So in other words, if I ask you what is the transfer function E of s by d of s, keeping in mind that Rs equal to 0, okay, so what do you get? So if this is the input output, so how do you move? You'll move like this, like this, like this, this. This is the path. And in this path, here you have a negative sign, right? So if I ask you to write this one, so because the negative sign you get, so if I assume this is, let's say, G of s. So what is this E of s by D of s? So this is basically how much you'll get? Minus of G of s, okay? minus of g of s only, right? This is what is the only thing you will get. So because if you are starting here, so this is what you are stopping here, right? So you'll get minus of g of s. Yeah, this divided by 1 plus the characteristic equation of the loop is basically 1 plus 10 g of s. So E of s is basically d of s, minus sign is there, into g of s, which is 1 by s into s plus 10 divided by 1 plus 10 gs, 10 by s into s plus 10. Okay, this is what the situation is. You can simplify this. This is minus of d of s. If I multiply these factors, it is 1 divided by, this is s into s plus 10, isn't it? So this is equivalent to minus of, this is 1 by s, and this is 1 by s square plus 10s plus 10. Because d of s is basically 1 by s, because dt is basically unit step input, that's what he said. So if it is unit step, dt is ut, then d of s is basically 1 by s. So that's why in place of d of s, I'm substituting here 1 by s. So this is what is your function e of s. So now you may substitute it here. So this implies e of infinite is equals to limit s tends to 0 s into e of s. So e of s value if I write, so that is minus 1 by s multiplied by 1 by s square plus 10s plus 10. Am I correct? Yeah. So if you see this and these are being cancelled, so this answer happens to be limit s tends to 0 minus of 1 by s square plus 10s plus 10. So s square is 0, this is 0. So this is minus 1 by 10, this is minus a 0.1. So this is basically minus 0.1. So this is a standard model questions which has been asked multiple times in the GATE exams. So basically by taking ds input and es as output, you have derived the transfer function e of s by d of s, and then by using final value theorem, we are getting the answer 0.1. So 0.1 is the right answer for this.